Good morning, everyone. So welcome to my YouTube channel, Maths Avtaram. Today we are going to see 7th lecture on Riemann integration. So in this lecture, we will study some sufficient condition for Riemann integrability. Okay. So let us start today's session now. Okay. Let F close interval AB to R be a function of be a bounded function. Be a bounded function. Okay. So UPF, how UPF is defined? UPF is nothing but infimum. The upper Riemann integral. How upper Riemann integral? How it is defined? This is nothing but infimum of UPF, where P is a partition of AB. Okay. So it means what does it mean? Now this is infimum. So it means what? Infimum, the each element is, so it is infimum. So what does it imply? It implies that if you take UPF, then it will be greater than this, because this is infimum. Okay. For any partition P of closed interval AB. Okay. And what is lower integral? Lower Riemann integral, and A to B fx dx is equal to supremum of LPF. P is the partition of closed interval AB. So what does it mean? It means this is supremum. So it means each LPF is less than equal to A to B fx dx. Okay. So let's say this equation is star. Okay. And this is for any partition P of closed interval AB. Okay. Let's say this is double star. So, but we know that small m times B minus A is less than LPF, UPF, and close interval B minus A. Okay. Close interval. And we have also proved, and we also know that this happens A to lower integral is always less than upper integral. Okay. So what we, let's say this equation number triple star. Okay. So from star, double star, and triple star, we get what we get? Okay. Because by triple star we have lower integral fx dx is less than upper integral fx dx. But by star we have UPF. Okay. And by double star we have this one LPF. Okay. Again by triple star we have this one. Again by triple star we have this one. So we have this formula, or you can say identity or inequality. For any partition P of closed interval A. Okay. So we will prove a result. Darboux condition. Theorem. This is called Darboux theorem. Darboux theorem. Okay. Darboux theorem for integrability, for Riemann integrability. Okay. Let F close interval AB to R be a function of bounded be a bounded function. Be a bounded function. Okay. Be a bounded function. Okay. So let me write. Okay. name is just a simple Darboux theorem. Okay, do not write here Riemann integration. Okay, that is correct. It is only Darboux theorem. Let me try it again. This is called this directly Darboux theorem. Darboux theorem. Let F closed interval AB to R be a function, be a bounded function. Be a bounded function. Okay. Then given any epsilon greater than 0, there exists a delta greater than 0 such that UPF is strictly less than A to B fx dx plus epsilon, and LPF is still greater than A to B fx dx minus epsilon. For any partition of closed interval, any partition P of closed interval AB with norm of P less than delta. Okay. So let's prove it. Okay. So let what is UPF? UPF is what? This is infimum of upper integral is infimum of upper integral A to B fx dx is equal to infimum of UPF. P is a partition of closed interval AB. Okay. Given any epsilon greater than 0. So you let epsilon greater than 0 here. Let epsilon is greater than 0. Then then there exists a partition P1 is equal to A x0 x1 x2. Okay, xp is equal to B. Okay, B of AB close interval such that U P1F will be less than upper integral fx dx plus epsilon by 2. This comes by definition of infimum. If you add some positive quantity in infimum, there will be some element of member in that set, that is UP1F. This will happen like this, and this will happen like this. Okay. Okay. Now let P be a partition. Sorry. Let Q be a partition of closed interval A B such that norm of Q is less than delta. Okay. Put P star is equal to Q union P1. Okay. Okay. Q union P1. Then P star has at most P minus P plus 1, P minus 1. P minus 1 is equal to P plus 1 minus 2. So how many points the P1 partition has? It has P1 plus P plus 1 points. But we are excluding AND points because Q is also partition. It will contain AND points. So how many more points? At most more points P star has. So it has at most P minus 1 more points. Okay. More points. Okay. More points. Then by the result from previous lecture Riemann integration lecture 6. Okay. We have okay. So first you put this thing. Do not write this here. Okay. You will write it later. Since F is bounded, there exists a greater than 0 such that fx fx less than equal to k for all x belongs to closed interval k. So put 2 p minus 1 okay k times 2k p minus 1 2k 2k p minus 1 okay delta is equal to epsilon by 2 okay epsilon by 2 because norm of partition is this okay okay then by a result in previous lecture Riemann integration Riemann integration lecture 6 we have UP1F minus 2k p minus 1 delta this is less than u p star f and that is u p1 f okay so they simply This implies UP1F UP1F minus 2K and so UP star F UP1F is greater than okay. 1 minute, let me check. So UP1F is greater than UP star F and that is 2K sorry let me here it has more points than Q. Okay, than Q. So it means P star contains Q. Okay, and it has at most P minus 1 more points. So by previous result, we will have here P star. Okay. So we'll have 2 minus. So by previous result, we will have this one. Let me write it again. We have this one. UQF minus 2K P minus 1 delta. That is greater than UP star F. Okay. Okay. QF. By previous result in lecture 6. Okay. So we have this one. Okay. Okay. So we'll take only this part. So this implies UP star F greater than UQF minus 2K P minus 1 delta. Okay. So what we have? So let's say it's equation number 1. But P1 is containing P star because P star is union of Q union P1. Okay. So this implies U P1F is greater than U P star F from 1 and 2. We have Okay, we have U P1F is greater than U2F minus 2K P minus 1 delta. Okay. Okay. Now what is this? What is this? UP1F is less than, let's say it 4 star. Okay. But from 4 star we have UP1F is less than upper integral Fx dx minus epsilon by 2. Okay. So this implies A to B Fx dx minus epsilon by 2 will be strictly greater, because this part is strictly greater and this is greater than, so this will be strictly greater delta. Okay. So solve it. So this implies you take, sorry, this is epsilon plus epsilon by 2. Okay. This is plus here. Plus here. So bring this part here. Epsilon by 2 plus 2k p minus 1 delta. Okay. So this implies A to B Fx dx. But this is also epsilon. So this implies UQF is less than A to B Fx plus epsilon. Okay. So but delta is greater than 0 because here A is greater than 0, P minus 1 is greater than 0, delta is greater than 0, sorry, epsilon is greater than 0. Epsilon is greater than 0. Okay. So this implies delta is also greater than 0. Okay. Okay. For partition Q of closed interval AB with norm of Q is less than delta. Let's say it equation number 3. Okay. Similarly, we can find a partition S of closed interval AB with norm of S is less than delta such that LSF is greater than A to B fx dx minus epsilon. Okay. So let's say equation number 4. Put P is equal to union. Okay. Then P contains Q. So this implies UPF is less than UQF. But this is strictly less than A to B fx dx plus epsilon. Okay. So this implies UPF dx plus epsilon. Okay. And because P contains Q, okay, since P contains Q implies norm of P is less than norm of Q, that is less than delta. Similar, and P contains S. Okay. Since P contains S implies norm of P, the norm of always greater superset is always less than subset. Less than delta. Okay. And what is this? And what we will have? We will have, when we take superset, the LPF always increases. LPF always increases. So LPF is greater than LSF, but this is A to B fx dx minus epsilon. Okay. Hence, G1 epsilon greater than 0, there exists delta greater than 0. such that UPF is less than A to B fx dx plus epsilon, and LPF is greater than A to B fx dx minus epsilon. For the partition of AB with norm of the rectangle. Okay. So today's lecture for this, if you have any program related to this, you can comment on my YouTube channel. Thank you very much for today's lecture. Thank you very much.